Yes, hello everyone. So in the first part we have proved that for any n less than 4000 the postulate is true. Okay, so now we are going to establish a contradiction using several facts. So we start by proving an inequality involving the product of primes. So it says that you take x be a real number greater than or equal to 2, then we are going to prove the product of all primes less than or equal to x is less than or equal to 4 power x minus 1. Okay, so we are taking the product all over the primes less than or equal to x, and that is less than or equal to 4 raised to x minus 1. Okay, so what we are going to do is we use induction on all the primes less than or equal to x. Okay, so assume q is the largest prime less than or equal to x. Now we can rewrite this product in the left side of the inequality that we have to prove is like this: the product of primes less than or equal to x equal to the product of primes less than or equal to q. Because we are talking about only prime numbers, so I can avoid the real number if it is not a prime number, so I can find the largest q. And also it is very clear from that, because q is less than or equal to x, definitely 4 power q minus 1 is less than or equal to 4 power x minus 1. Now if q equal to 2, the result is true, because the only prime available is 2, so that is less than or equal to 4 power 2 minus 1, which is 4 power 1, 2 less than or equal to 4. So the base case is true. So now we assume that this is less than this inequality is true for all primes except q, because q is the largest one. We need to prove it is true for q. So assume for all element less than that, for all integers less than that, the result is true. So now let us assume q is a odd number, because the only even prime is 2, so q can be written as 2m plus 1 for some m positive. Okay, so here we may assume the induction, that's the inequality is true for all elements in between 2 to 2m, because 2 is 2m plus 1, 2q minus 1 will be 2m minus 1, because x is a real number, right? So it has to be true for just less than q. Okay, the integers is true for integers. So right, so let us write our products, because the product involves only primes and natural numbers, so that's why we avoid the strict real numbers less than q. Okay, so we can write this product p less than or equal to 2m plus 1. Okay, which can be factored into two products. First, all the products less than or equal to m plus 1, because all the primes we are taking n plus 1. Then after that we write to we taking the product of primes which is greater than m plus 1 but less than or equal to 2m plus 1, right? So now we are going to prove that this is the inequality is true. So this is the left hand side of the desired inequality, p less than or equal to q, which is 2m plus 1. So before that, let us estimate the second factor here. So we will say that the second factor is less than or equal to 2m plus 1 choose m. This is because 2m plus 1 choose m is nothing but 2m plus 1 factorial divided by m factorial times m plus 1 factorial, because we know that we just use the formula of nck, n minus k factorial times k factorial, right? Yeah. And always now note that 2m plus 1 factorial is nothing but 2m plus 1 times 2m times up to 1. So this numerator contains all the primes less than or equal to 2m plus 1, right? Yeah. So in fact it contains all the primes in between m plus 1 and 2m plus 1 also. But if you look at the denominator, they do not contain any primes of right. So you can see p is in between m plus 1 and 2m plus 1. So those primes will not come in the denominator, right? Because in the denominator the possible primes are less than or equal to m plus 1, but that is not available in this product. Okay, so all these primes are only available in the numerator, right? And multiplied by a positive factor, that then definitely this inequality is true. Okay, so that's the idea. Now yeah, so that's what we say. So finally we make one more estimate, that is this fellow 2m plus 1 choose m is less than or equal to 2 power 2m. Now why it is so? Because we know an identity nc naught plus nc1 plus up to ncn is 2 raised to n, right? Now you replace n with 2m plus 1, then what do we get? We get 2 raised to 2m plus 1, right? So we get this thing, k equal to 0 to 2m plus 1, 2m plus 1 choose k is equal to 2 raised to 2m plus 1, coming from this formula. And you have to notice that these two fellows are equal. 2m plus 1 cm choose m, and 2m plus 1 m plus 1, they are both equal, because you know nck is equal to ncn minus k. So 2m plus 1 m is equal to m plus 1 is equal to 2m plus 1 minus m plus 1. So what is left is just 1m. So that is this. So this is equal to 2m plus 1 choose m plus 1 equal to 2m plus 1 choose m. Okay, so now look at the sum here. In this sum they both are equal, so I can rewrite the sum like this: 2 times 2m plus 1 choose m plus a factor a equal to 2 raised to 2m plus 1, because these both are available as a summand in this particular sum in the left hand side. So I can replace one with other, so you get 2 times of this plus a equal to 2 raised to 2m plus 1. Now we divide it by 2, then you get 2m plus 1 m plus a positive factor is equal to 2 raised to m. So that means this should be less than or equal to 2m plus 1 choose m less than or equal to 2 raised to 2m. That's what we have said. Using these all facts, we go back to the also by induction hypothesis. What is induction hypothesis? Whenever it is less than q, that satisfy the idea. So it is m plus 1, so this product is equal to 4 raised to x minus 1. So here we have x equal to m plus 1, so m plus 1 minus 1 is m. So you get this is directly from the induction hypothesis. So using these three inequalities, we can go back to the original one. So product p less than or equal to p equal to, we have found that these are two factors. Now we estimate both. We estimated this, that is 4 raised to m. Next one we estimated, first we estimated is less than or equal to 2m plus 1 choose m. Then we estimated it is less than 2 raised to 2m. So together we can write it is 4 raised to 2m, right? Because 2 raised to 1 is 4 raised to m, so by exponential rule 4 raised to 2m. So that's the equation, because q is equal to 2m plus 1, then you got that it is less than or equal to 4 raised to 2m plus 1 minus 1. So our by induction this is true for q. Okay, I mean true for every x, because we able to prove that it is true for q. Okay, so that is what we want to what is the second step in proving Bertrand's postulate. Okay, yeah, that's part 2. Okay, so next thing we need an idea of Legender's theorem, which is in fact counting prime factors in n factorial. Yeah, how many times p appears, the largest power of p in n factorial. That is the, so we will go for a proof and all. So this is the idea. So basically in the second step we proved an identity, an inequality, which is tells you the product of all primes less than or equal to a real number x is less than or equal to 4 raised to x minus 1. Because it is 4 raised to x minus 1, of course is less than 4 raised to x, because you multiplying both sides a positive factor. So just keep in mind, we use both ideas whenever necessary. Okay, thank you.